Hey everyone, welcome back. It's day 5. We're gonna be doing some Advent of Code today. So glad to be here, so glad. Hope you all had a wonderful, I don't know, what day is it? Tuesday. It'll be Wednesday when this video comes out. Hope you're having a wonderful Wednesday, or whatever day of the week you decide to watch this thing. Let's switch on over to Advent of Code. If you haven't seen the last 4 videos, go check them out. There's a playlist every day for the past 4 days. I've been doing Advent of Code problems in Elm. So over here we have Advent of Code. Let me unpin this so you can see how we've been doing it. Is I've been writing code in Elm, hitting the compile button, and we've been walking through solving Advent of Code problems step by step. So you probably get the spiel if you're watching day 5, so let's dive right into it. This is the first time I'm going to take a look at the problem, and I'm just going to walk you through how we can solve it using a functional programming language. All right. Day 5. You take a boat and find the gardener right where I don't even remember. Like, literally, this was yesterday. I don't know what's going on. We got a gardener here. It's a giant garden. Looks like a farm. At a stop because we ran out of sand. Can't make snow with dirty water. Okay. Something. You barely have time to agree when he brings up another request, I guess. While you wait for the ferry, maybe you can help us with our food production problem. The latest Island Almanac just arrived, and we're having trouble making sense of it. The almanac, our puzzle input, lists all of the seeds that need to be planted. It also lists what type of soil to use with each kind of seed, what type of fertilizer to use with each kind of soil, and what type of water to use with each kind of fertilizer, and so on. Every type of seed, soil, and fertilizer, and so on, is identified with a number, but numbers are reused by each category. That is, soil 1, 2, 3 and fertilizer 1, 2, 3 aren't necessarily related to each other. So here we've got seeds. We've got a seed to soil map, a soil to fertilizer map, and a fertilizer to water map, a water to light map, and a light to temperature map, and a temperature to humidity map, and a humidity to location map. So the almanac starts listing which seeds need to be planted. So that's these guys. The rest of the almanac contains a list of maps to describe how to convert numbers from a source category into a destination category. The section starts with seed to soil, describes how to convert a seed number to a soil number. Seed number to soil number. I wonder why there's 3 digits. Rather than list every source number and its corresponding destination, number 1 by 1, the map describes entire ranges of numbers that can be converted. Okay, so we have the map contains 3 numbers: the destination range start, the source range start, and the range length. So consider again a seed to soil map, 50, 98, 2. Destination range start of 50, a source range of 98, and a range length of 2 means that the source range starts at 98 and contains 98 and 99. The destination range is the same length, but it starts at 50. So 50 to 51. This information knows that seed number 98 corresponds to soil number 50, and that seed number 99 corresponds to soil number 51. So I guess the offset from the centers matter. So this looks like it's the same as typing 5199 underneath it. The second line means that the source range starts at 50. That's the second line here. And contains 48 values, 50 all the way up to 97. This corresponds to a destination range starting at 52 and also containing 48 values, 52 to 99. So seed number 53 corresponds to soil number 55. So any source numbers that aren't mapped correspond to the same destination. So seed 10 will correspond to soil 10. So the entire list of seed numbers and their corresponding soil numbers looks like this. 0, 0, 48, 48, 59. And as soon as we get to 50, we go to 52 because of this seed map offset. That continues to be true until we hit, 97? Yeah, 99, and then we go back to 98. Sets the 50. This is a really weird way to represent information. So with this map, you can look up the soil number required to match each initial seed number. So seed 79 corresponds to 81, 14 corresponds to 14, 55, etc. So the gardener's team want to get started as soon as possible, so they'd like to know the closest location that needs a seed. Using these maps, find the lowest location number that corresponds to any of the initial seeds. To do this, you need to convert each seed number through other categories until you find the corresponding location number. So we're going to go through this whole thing until we have a location. So we're going to keep repeating that process. So 79 maps to 81 to 81 to 81 to 74 to 78 to 78, and then finally to 82, all the way down. The lowest location in this example is 35. So what is the lowest location number that corresponds to any of the initial seed numbers? Oh my goodness. We're going to get some parsing going on. We're going to get some weird, confusing math. This will be a fun puzzle today. Let's take a look at it. So I'm going to copy this input, this puzzle input. We start everything with this. And what we're going to do is we're going to compile. This is our input. It's all just a big blob of text, and it's going to be up to us to parse this and break it into useful information. So what I want to do is I want to just start by taking this, trimming it, and then I think we're just going to have a function that turns it to an almanac, which is what they were calling kind of this data structure that we have. So let's get started. Let's turn this crazy string in a data type that we can understand. So what's an almanac? Almanac has seeds, which are just a list of integers. It's going to have a list of converters here. So seed to soil, soil to fertilizer, fertilizer to water, etc. So I'm going to type all those out. So seed to soil. It's going to be a dictionary that matches seeds to soil. All these are going to be numbers. So we're just going to do int for all that. Soil to fertilizer, is that what it was? Fertilizer. Boop. Fertilizer to water. Water to light. We got light to temperature. We've got temperature to humidity. Cool. Oh, sorry, and then one more, humidity to location. So we could represent it like this. We could also represent it as a list of maps. I'm inclined to start with this and then see if it should just be a list of things that we kind of loop through. But let's just see if we can parse this information and get something reasonable. So the way we're going to do that is we're going to start with a function called toAlmanac. Almanac. It's another one word where as I type it, I'm like, this is nuts. So we're going to have raw text, and we need to do something to that raw text to change it from here. So I'm just going to format this, hit compile, and see what's messed up. So I need to make sure to import the dictionary data structure so I can refer to it in our type annotations. Yeah, cool. Okay, so we start with that raw text. So what we want to do next, I think we want to split this string up with any like double new line. So what we're trying to do is break this into a list of strings so that we can have each section kind of isolated. And then what I want to do is map each of these lines and just get the numbers here. Just get the space separated numbers. And in this case, I want to get multiple lines. So this is our, I'm going to call this, I'm going to scroll down here and I'm going to give us a bunch of space so we can start to write some code here. Sections. Do is take those sections, so that's where we left off, and I want to be able to let's just start by just getting these seeds. So do this where I say seeds, and the rest Here, if I have an empty string, I can't do anything with that. So if there's nothing in my map, I'm out of luck. But with seeds, what I can do is I can say, let's see if we can just get that highlighted part. The way I would do that is I would say string.drop left seeds, colon space, however long this word is, so string.length of that. I want to drop that from the front of the seeds string. So I think that would give me just these numbers here. Perfect. So those are my seeds. So here, if I run that through string split spaces, and then I can do so if I split it on spaces, I'll get an array of these strings, and then I'm going to run that through a list filter map. We used this in previous videos. Let me mute my phone here. To turn this will turn our strings into numbers. So now we've got a list of our seeds, and these are just the seeds. So what I'm going to do is I'm going to do another format. Notice all these parentheses I have here. A way we can get rid of that is we can move some things to the pipeline. If we wanted, we could take this, make that a variable. But I think I'm okay with this actually. So we've got our seeds. So that's part of the thing that we want to return. So I'm going to say that the seeds is this. And so our almanac is going to need all this stuff also. So in order for me to return all that information, we're going to want to make sure we have something that can take a certain index into this map and just give us the map like separated lines. So the code for scanning this is going to be the same code for scanning this and this and this. So what I think I want to do is I'm just going to use the index into the map string and try to do that. So I'll say to mapping, I guess is what we'll call it. And I'm going to say what the index is, and I'm going to give it the map string. So let's try to make this function here. So how to mapping is going to work is if we give it to mapping is going to take in a string, and it's going to take an index, and then it's going to take a list of strings. We're going to return something, list of strings. Sorry that the text is gray. Sometimes this happens in Ellie. So what I want to do is I guess this is a list of other strings. List of other strings. I think I want to do is instead of returning all of this stuff for seed to soil, what I want to do is take the item at that index. So I'm going to say list dot drop index and grab the head. That's a way you can do that with a linked list. So here I have the I'm going to drop nothing from the front. So here I've got the seed to soil map. I could repeat this process for all the other listings. And what that would look like is I would have all of these as my keys. Always off by one. So this first part of the problem is we're just parsing the information and putting it in a data type that we can kind of loop over. I have a feeling like I should have just made this a list instead of giving each field a name, but this might be nice when part 2 shows up. I don't know. So this is where we're at right now. We're running this code on all of it, and all we're getting is strings. So what we want to do is we want to split this into new lines. So we're going to do a maybe.map, do a string.lines. So if we do have a string, we're going to split it. So we have the first map. We're going to have 49 to 53. We're going to have all those numbers. So I'm just going to say maybe with default. so that we can get rid of all this maybe mapping here. And I'm going to say, if we got this far, that's fine. Let's get rid of the maybes. So now we have this for each map. I'm going to say list dot drop 1. Does that work? Yep, 1. So now all we have is these maps. And then for each element in the list, we can say list dot map, list dot filter map. It's actually going to look a lot like this here. This function. This is going to be split and convert to number. So that code, we're just going to reuse it. Call that split and convert to number. So if you give me a string, you could pass that in. It's going to split it on spaces, and it's going to convert it to a list of numbers. So just to make sure we have the types right, I'm going to do that. Compile. And then here, instead of calling the filter map, we're going to just call split and convert to number. So here we've got a list of 49, 53, and 8. So what I wanted to do here is, in order to return this as an almanac, I wanted to make it so that if you looked up a certain number, it would give you a certain mapping. I don't know if I want to enumerate this in the dictionary. I think I might just want to make a data type called mapping. And that will hopefully prevent us from hitting performance issues from me enumerating all the things. So we haven't done this before, but what I'm going to show you is a custom type. So in Elm, you can make these custom types that secretly hold on to information. So here, this is secretly holding on to a list of lists of integers. So by doing this, by passing this through mapping, this is kind of the constructor. So I can like halt that if we want. It's a convention in Elm to name these things the same thing, which can be a little bit confusing for beginnings. But for beginners. But the important thing to know is that these two values need to match up. If this was called banana, the code would still work because banana is the type, which we'd use up here, whereas mapping constructor is just is one of these variations on here. Normally types have like, red or blue or stuff like that. So in this scenario, I guess we don't need a custom type for this. Maybe this is overkill. What we want to be able to do though is say that a mapping is really just a nested list of numbers here. So we can call it that. We can say to mapping takes an int, takes a list of strings, and it should return a mapping. And then this type alias just kind of serves to help us with annotations. So if we wanted, we could make it a custom type. I don't think we're going to actually see any benefits of that. But if we were making a big Elm project, it would be nice for this module to get its own data structure, its own collection of functions. But that's more advanced, like Elm code architecture stuff that isn't too relevant when you're editing everything in a giant Ellie file. So there's your tangent. All right. So what we have here is all the information we want. I'm going to make functions that are kind of centered around this mapping type. And like I was kind of hinting at earlier, if I was making a big like Elm project, mapping would be its own file. And we would have functions that allow me to like give a number and then like look up, like given a mapping, I'd be able to like look up like what's the destination. So from source to destination, you would give it a source number, you'd give it a mapping, and then from there, it would always be able to give you a destination number. So this is the part where we would do the logic. So by default, if we had like an empty map, we would just return whatever number we got. This is where the crazy logic starts to happen, where they're talking about reading the 98, adding 2 to that. If it's within the range 98 to 99, then we're going to take this and add whatever that offset was. And if we don't find a match, then we'll just return the source number as is. So the code to write that isn't so difficult. It's just talking about it in English is really confusing. So what we're trying to do is we're trying to make one function that, given a mapping and giving an input number, spits out an output number. So I think we can do that just by using these ranges. Um, so let's see how that goes. Okay, source mapping. So what I want to do is say mapping list dot filter filter map. So we need to find a match. So find match. We're gonna make this a local. Let's make it its own function here. We can do find match. We're gonna give it the source number here. And what we're gonna do is, since this is a list, what we want to do is we're gonna want to take in each match one at a time. And then, yeah, we're going to want to take each match, we're going to give it the source number, and then we're just going to give it our list of integers here. And we're kind of hoping that these numbers are always 3. So maybe we're not quite done with our mapping. Maybe this should be something more helpful. Like instead of a list of integers, maybe we shouldn't leave off here. Maybe we should have a source, start, and use all the terms that we saw in the puzzle. So I think I'm jumping ahead a little bit too far. What we want to do is we want to make a object that has source range start, range length, and destination range start as its fields. So destination start, and then range length. All these will be integers. And really, a mapping isn't valid if it isn't a list of these specific types. So here, what we want, we're going to have to come up with a good name for this. So mapping is I'm going to call this a range map. Call it a range mapper. This is all just kind of made up words to help us annotate our code. I might come up with a better name than that later. But the idea is, instead of having a list of ints for our logic, we would see if we could find a match for that range mapper. Then from here, we'd have access to source start, we'd have access to destination start, we'd have access to the range length, and we'd be able to do our logic and determine, like, is there a match? Yes or no? If so, give me the first one, and then if not, just spit out the source number as is. So this is kind of the high-level logic we want, but if I hit compile, it's not going to work because I promised a mapping, but here I'm returning a list of lists. So what we want to do is we want to say list.filter map. Each individual item, we want to turn that to a range mapper from a list of ints. So if we're going to make one of these, we just format this. Given a list of ints, it's only going to be valid if we're able to turn it into a valid range mapper. So luckily, this code is easier to write than you might think. All we have to do is there's going to be the, what's the order? I think starts with destination, then source range, then range length. So that's the order that we're going to parse it out. We're going to say destination start is the first thing we expect, then we expect the source start, then we expect the range length, and then we expect nothing else. We expect a list with exactly 3 numbers in it. And if we get that, we'll be able to create this data type here. So I'm just going to copy these. I could use the type alias as a constructor, but I'm going to choose not to do that for readability. There are certain conditions where I do it and certain conditions where I think it can lead to more bugs by getting fields out of order. So I'm going to leave that like that. And so if there's exactly 3 numbers in our list, perfect. If not, it's not valid. So we're just going to ignore it and filter it out. So now you'll notice that our fertilizer to water mapping isn't a list of numbers anymore. It's got these really nice range mapper things here. And so all this code here is compiling. What we want to do is we want to start with each seed. So where are our seeds at? They're like floating in the middle here. We want to start with each seed, and we're going to want to do a lookup here. Um, so what I want to do is I want to test that our logic is right before I run it on the whole. This is a big block of information. This is like our almanac. So what I'm tempted to do is to split this into two different problems. So saying like uh, almanac, this is going to be, which is a maybe almanac. Let's just pretend it always works here, just for our type annotation. And then if it fails, what we can do is we can just say it's an almanac with no seeds, no seed to soil, no soil to fertilizer, no water, no light, no temperature, no humidity mapping. And this will allow us to just call this an almanac and get rid of the just in the beginning, as well as have this be a data structure that we'll be able to use later. So I'm going to put the annotation back on for folks following. And I'm just going to move this below. So here we have our almanac, we have our way to parse it. I'm going to move the puzzle input here. And I'm just going to put it at the top. This will make it easy when we need to put in the custom puzzle input that we get. Everyone's AvenaCode puzzle is going to be a little bit different, so it should still be good. Okay, cool. So right now we're printing out the whole almanac, but really what I want to do is I want to say, let's test out this function just to make sure that we're doing things right. So if we call from source to destination, we give it a seed, and then we give it one of these mappings, it should spit out the right answer. So let's use the examples that we saw in the problem to make sure that we're following along correctly. So here, if we take the soil seed to soil mapping, if we take the seed to soil mapping and we give it 0, we want this thing to spit out 0. So give you 0 for this, and then we take the seed to soil mapping. Let's see what it gives us. So 0 is mapping to 0. I'm going to snap this over here so we can kind of do this one step at a time. So if I some multiple lines, this will make it easier to test. So 0 is 0. It looks like 1 is mapping to 1. Let's try 50 and see if 50 is mapping to 52. So 50 is still mapping to 50. So we didn't add the code. Oops. It's a string and returns a maybe almanac. I have to add that. So we didn't add the code that actually scans and tries to find a match, right? Remember down here we said always return nothing. So we didn't add that logic in. So let's add that logic in real quick, and then we can test and see if 50 becomes 52. So what they were saying is that with each line, you're going to take the source range, you're going to see if the seed that you gave is within the range. So is this 98 or is this 99? That's like the length we have here. So we're going to say if the source is greater than or equal to the source start, and source is less than or equal to source start plus the range length, but minus 1. Because 98 plus 2 is 100, we want to subtract 1 to make sure that we're in the 99 range. So if it's greater than or equal to 98, but it's less than or equal to 99, then we did find a match. What we want to do is we want to find the destination start plus whatever the offset is here. So the offset, if it was 50, the offset would be 0. If it was 51, the offset would be 1. So the way we're going to figure that out is we are going to take the source, we're going to subtract the source start. That'll be the absolute offset. I think that's right. I think that's all we need to do. So if we gave it 50, 50 minus 50, gave it 50, or sorry, if we gave it 98, 98 minus 98 is 0, so 50 would be the output. And then if we give it 99, 99 minus 98 would be 1, so 50 plus 1 would give us the output we want, which is 51. Okay, so I think that's all right. So this is what we want to do here, but if the source is out of the range, that's when we do nothing. So I'm going to take all that math and I'm just going to format it like this. I'm going to do double parentheses here because I think that'll prevent Elm format from making it go on a new line. So hopefully all that work, what we'll see at the end is that when we hit compile, we're going to get 52 instead of 50 on the right. And we do, so that's good. Let's make sure that 0 is still 0. I forgot that we hadn't tested that. And then let's just test one more thing. Let's test that 99 is returning 51. And then I'm feeling pretty good about this code. Great. So looks like all that crazy stuff we wrote, including this, and doing all the mapping 0, 1, 2, 3, 4, 5, 6. Just wanted to make sure that it was reading the right index in the right order. Looks like all that stuff is working. Looks like we have all of our logic for checking it. But what we need to do now is we need to start with our seeds. So let's start with our almanac seeds. And let's solve our problem one step at a time again. So we've got a list of seeds. So for each seed, what we want to do is we're going to want to call from source to destination. And we want to take in our input, basically our source here. We want to take that source and we want to give it almanacs, or almanac.seed to soil. So that would convert all of these into their numbers, and then we're going to repeat that process. This is the silly way to do it. We can use a list to loop through it. I think that's what we're going to end up doing for the part 2. But what I'm going to do just to show you is we're really just calling this function, taking all these seeds and transforming the values 1, 2, 3, 4, 5, 6, 7 times. So 1, 2, 3, 4, 5, 6, 7 times. What I'm going to do is I am going to do a multi-line copy, do a multi-line paste. So soil to fertilizer, fertilizer water, water to light, light to temperature, and then at the end of this, we have 82, 43, 86, and 35. And I think that was what we ended up with here. 82, 43, 86, and 35. 82, 43. I don't think we had a... Yeah, 82, 43, 86, 35. Yep, that looks right. So all we're going to do is find the lowest number. If we have a list of numbers and we want to find the minimum, Elm has a built-in list.minimum function. So the answer is just 35. That is what the puzzle input is expecting. So before I grab my puzzle input, what I'm going to do is I'm going to go here. I'm going to say day 5, part 1. And then I'm going to click save. And I'm going to copy this here. I'm actually going to duplicate this. And this original solution will be in the description of the video. So you can click the link for part 1, and it's going to have this code. Let me just pin that so I don't lose it. And this has our answer. What I'm going to do next is I'm going to get our puzzle input. So by ours, I mean mine. And I'm going to copy this. This is why I'm really happy that I didn't enumerate the dictionary. I just did offsets. Maybe these numbers will overflow. Hopefully we can handle it. I might end up needing to do floats instead of integers to prevent integer overflow, but we'll see. Do a compile, and my answer is a really big number. Let's see if it's right. I'm afraid that my numbers are too big. Nope, numbers were not too big. It did not go above the maximum size of integers, so we're good. We got that one right, so that's great. What we're going to do next is we're going to take a look at part 2, and part 2 is going to be a little twist on the problem, and we'll see how it goes. So continuing to part 2. Everyone will starve if you only plant such a small number of seeds. Rereading the almanac, it looks like the seeds line actually describes a range of seed numbers. The values on the initial seeds line come in pairs. Within each pair, the first value is the start of the range, the second value is the length of the range. So in the first line of the example above, 79, 14, 55, 13, this is actually describing 14 values, 79, 80, all the way through 91 and 92. The second range starts with seed number 55 and contains 13 values. Okay, so 79 is the start, and then 55 is the end. Now, rather than considering 4 seed numbers, you need to consider a total of 27 seed numbers. In the example above, the lowest location number can be obtained from seed number 82, which corresponds to soil 84, fertilizer 84, water 84, light 77. So the lowest location ends up being 46. Consider all the initial seed numbers listed in the ranges on the first line of the almanac. What is the lowest location number that corresponds to any of the initial seed numbers? Okay, so it's just changing one thing, but I know it's going to be scary because if you look at our seed numbers, those are pretty big numbers. So what we're going to need to do is compute this lookup for a ridiculous amount of numbers, millions of numbers. Oh my gosh. Find the lowest. Maybe I can handle that. Let's see. All right, so we're gonna call this part 2, so I don't get confused. I'm gonna save this. Undo this. I'm gonna save this. So what it's saying is we left off um, here with 35. That was our answer, but our seed parser was wrong. So the logic that we did when we did 2 almanac, where we just took the seeds and then we dropped the beginning and then we split and converted that to a number. What I think we want to do instead is we want to take these seeds, we want to split them by spaces still. We want to group them by 2, and then we want to have a start and then a range represent our seeds. So we're going to change the data type here for the almanac to be a list of start numbers and then range numbers. So 13 total numbers. So I just want to make sure that I get this part right. So contains 14 values, 79 all the way to 92. So let's do that one step at a time. What I'm gonna do is I'm gonna go back up here, and we have all this code that kind of runs through and does the calculation. So this is gonna be find nearest location. So that's the exact same code we had from before, but find nearest location previously was working on a list of seeds. Nearest location. Yes, what we want to do is we're going to want to have each individual seed. We used to have the seed be a string. Now I'm going to get rid of all these list.map prefixes. So we're not working within a list anymore. We just make sure that this code still runs as expected. Do that. Just moving that so we're not mapping through so many things. Looks like I screwed something up. Oh, let's just take this out for 1 second. So, okay, 35. So we still have the right answer. This is where we left off. My nearest location. We just refactored the code a little bit so that we can start with an integer and then use that integer to find another integer. This was the old signature for the previous problem, but now we don't have an integer. That's not what our seed is. So if we called this a seed, previously type for seed was just an int. So this would still be the same answer. But now we want to change what a seed is from an int into one of these starts and ranges. So I think the way to do that is to maybe just keep this as, yeah, we don't want to keep a whole list. What we want to do is we kind of want to reduce and keep track of the minimum distance. So what I'm thinking is, for a given number, so for a seed number, seed, keep that as is. What we want to do is we want to have this function kind of run on a loop. So we'll come back to this, but what we need to do next is we need to make it so that this isn't an integer anymore. It's this data type. So if we compile it right now, it wouldn't work because we're saying that we're giving it a list of ints here, but we need a list of seeds. So I'm just going to comment this out. And then here we'll see that there's an error because I gave you a list of integers. But what I need to do is one last step, which groups those integers together. So what I want to do for that is, I think I want to use a package for this, list extra. So I think a list extra has a group by function built in. So if we open this up, take a look at the docs, you can say groups of 2, and then it's going to group everything together. So if we're going to do this step by step, I think the best way to do that is to stop promising an almanac here. Sorry that there's this crazy big tooltip there. So we're not going to say we're returning an almanac. And all we're going to do here is say that we're going to return something that has seeds. And we're going to do list.extra.groups of 2. That works. Oh, I need to import list.extra. So when you install a package, you got to import it. So that was the part I forgot there. And then, yeah, that's fine. What's wrong with that? Oh, the default is giving me trouble now. So let's do this. Let's do this. Let's do this. I don't really care anymore. Seed to soil. Okay, all this is going to be a big pain. Sorry, as I'm like halfway through doing the code, all the code that I was using before being upset. So what I want to do is really just a maybe map for now. So we'll make it better in a bit. But all we did here was it was a bunch of BS, but all I actually got done was I grouped these numbers. Previously, they were all in one continuous list. So what I did here was I just grouped them by 2. That we can do is we can do a list filter map, say 2 seed. So it'll go through each thing and it's going to turn the 79 and the 14 into a seed value that we can use. So if it succeeds, it'll be a seed. If not, it'll be a failure. Lint int. I mean to type list int. Maybe we'll get a seed back. Maybe we have an invalid input because it is a list. So what we'll do is case list of the first. So what was it? How did they order it? It's the seed number, so the start, and then the range. So those are the 2 things that we want to pull out. So start, range, nothing else. Then we'll have the start, the range. Making these fields makes it easier for us to handle stuff in our logic. We're kind of pushing the parsing out of the main code, which is nice because there's plenty of logic that we have to write to make this work, and we don't want to clutter that with bad information. So now that that's working, you'll see that we have range, we have start, and that should be good. And then what we can do here is we can add back in those annotations that were giving us trouble before. So now we no longer need the maybe map. So that was just a temporary thing I had to do while we were kind of showing our progress. Cool. So what I want to do is bring this back in. That'll work. This is good. So find nearest location. It's going to be find location. It's not really the nearest anymore because we're not doing the minimum. And then what we're going to do is we need to take these and we have to loop through. And because the numbers are so big in our source output, we don't want to like make a huge list and then find the minimum. What we want to do is just keep track of the minimum number and say, hey, if we're less than this is our new location. That way we're only storing one integer. I think the challenge of today's puzzle is managing memory in that way, not like pointers or anything crazy, but just making sure that we're not accidentally scaling things out of control. I've gotten bitten in the past by being reckless with like my memory footprint in some of these admin code problems. I think 2022 or maybe it was 2021. There's something about like a fish where I made like millions of fish and crashed my computer. All right, so we're going to start with these seeds. And what we want to do is we want to go through each seed. We want to keep track of a minimum value. So I think find nearest location is actually a great name for this one. And then we'll call this one toLocation, just to make it clear that these are two different functions. And then here we can say basics.int. I think this actually got moved to the random package. I don't think basics has a max int value. We can go check the docs. But max, yeah, basics max is not a thing, but Elm does have a random package where the max int is a value, and this is the maximum that we're going to use. It's just a call number. I don't want to call that number. I don't know who would pick up. All right, so this is our maximum integer. So I'm just going to call this max int. Folks reading the code back home. We're just going to leave it like that. So we're going to start with a crazy big number, and we're going to say that's our seed. And then hopefully we don't get higher than that number, otherwise we're going to be in trouble. So what find nearest location is going to do is it's going to take in a seed one at a time. It's going to take in our current maximum, and it's going to return the new maximum. So given a seed that has like a start and a range, and given the current max, we need to just decide what's the new maximum. So if we just ran this code, it's just going to spit out the maximum as is, because no matter what seed we get, we always just return the max that we had. So we loop through all the seeds, we don't do anything, and then we just spit back out the max. So this wouldn't be the right solution. What we want to do is, oh, sorry, this isn't the max. This is the minimum. This is the lowest number that we can have. So what we want to do is we want to do, I think, a bit of recursion here. We can say if the start, I guess if the range is 0, then we'll just return the minimum. That'll be our base case. And so what we're going to do is we're going to say, if we're able to do math, what we want to do is take that location. This is going to be our number. Take the location. We're going to take the start. We're going to add the range to it. That'll be our input. And then we'll say if the number is less than the min, then we're going to find the nearest location. We're going to say the start is the same, but the range is going to be decreased by 1. So it'll keep looping through. If the number was less, the new minimum is the number, and then if the number was more, or if it was the same as the minimum, I think this is the logic we want. So we're going to keep the old min in the case that the number is not less than the min. Let me hit compile and see if I'm range -1. Oh, I didn't add a field here. So 46 is what it's saying is the lowest. Is that what the answer was to the puzzle? Okay, looks like it was. Okay, so I'm going to save again. All right, knock on wood, fingers crossed. Let me format this. That this is enough performance-wise to work with our puzzle input. So I'm going to save this. That's going to be in the video description below. And then what I'm going to do is I'm going to take in our puzzle input, and we're going to try it. try our code on that and see how it went. Nervous about these big numbers. Oh, all right. Computer fan just kicked in. It's going through just a crazy amount of numbers. I'm back. We've got it. It's figured out. So let me show you what the solution we ended up going with was. And by we, I mean me. And we'll walk you through it. So as we saw before, this is all the code you just saw. When we run it, it's correct. But the issue is when we put in our puzzle input, these numbers are huge. Basically, if you take all of these numbers and add them up, that's how many numbers we end up processing. It was like 2 billion or something like that. So definitely couldn't run that in a web browser. So there was one trick that I found that made this possible to run. And the trick was instead of running, let's take a look at our code. Instead of taking these almanac seeds and running all of them within one program, the idea is if I find the value for like 79 and I find the value for 80 and I find the value for 81 and I keep incrementing upwards, it doesn't matter if I ran that all at once or if I ran that over the course of 27 different programs and then took the minimum of the output of those. So the idea is instead of taking all these numbers and just throwing that into the web browser and trying to get it to run it, we can actually just start at this number and we can take little chunks, little runnable chunks that will actually work with our memory constraints in the computer. And so if we ran these all in parallel or if we ran them sequentially, the result of the output of all those programs, we would take the minimum of it. And so we can kind of batch the work together. Maybe we find for this first part, we find what's the minimum here, what's the minimum there. And then we just have to take the minimum of all of those results, and that's the answer to the puzzle. So with this video, I'm going to include the normal part 1 and part 2 Ellie. This is the code that we used. The only big change that we did was I changed this main to take the seeds kind of as an input here. So instead of passing in a list of seeds, what we're going to pass in is a single start and a single range. And the way that we ended up doing that was we made an Elm program. We passed the seed in from JavaScript as an input. And what you can do with that is if you use platform.worker, we can add that to a node script that takes in the seed as flags and just runs our code for us. And the only thing we have to do is just return a fake model and then use something called ports. So I could type it all here. That would work. We just had like an empty like update that wasn't doing anything and an empty subscriptions that wasn't doing anything. But instead of running this in the browser, and I'm gonna leave this as is, I'm not gonna mess with this code here. Let me just undo all that. The idea is we're gonna pass that information in one step at a time into chunks that are runnable. So in addition to the Elm code that I showed you, I'm also gonna include a gist link to a JavaScript file that I used to basically take the exact program we wrote together and just run it in little bursts. So let's do a quick overview of what that looks like. As you can see, the program is still running. We'll get back to that at the end. But what we did was we took our Elm, we compiled it to JavaScript, and then we took our seed pair inputs. And I wrote this little function here that if you give it a start range or a start value and a range, and you give it a size to break it into, what it does is it breaks it into a bunch of smaller seeds that we can actually run. So instead of running 2 billion numbers, we're only ever running 100,000 numbers at a time. So as you could probably see by this, that resulted in us running the program 23,000 times. But what was cool about that was I wanted to watch a movie with my fiance, and I didn't want to keep trying to figure out a cool math way to fix this. So the way I solved the problem was I said, the code's good, I just need to run it longer. So what I did was I took the input, we broke it up into like parallel parts that we could work with, And so what we did was we took all those seed pairs, broke it up into chunks. I just had basically a list of 23,000 programs that we wanted to run. And then we just ran our Elm app and passed in those seed values, that start and that range value. Um, and we used all the code we had before. And so this was a little main script that I was using, and I have some console logs here so I can see the status over time. And this paid off really nice. I was printing out the most recent minimum as I went, and so I finished watching a movie, came back in here. I'm about to head to bed. I got to upload this video and then I can go to bed. But what was cool about printing the minimum was even though we're not finished running the whole program, I was able to just take this, this 177 number and plug it in and say, hey, did I find the minimum in the first 15,000 of 23,000? And I plugged it into the program or plugged it into the text box, and sure enough, it worked. So that's huge. We did it. Day 5, it's fixed. So I'll include the links to all the code below. I'm glad that I was able to break down the input. I wonder if that's the actual smart person solution. I don't know. I feel like there's a smarter solution out there. But yeah, I'm glad we made it. I'll be back for day 6, but right now I'm very tired. So good night, and I'll catch you later.